you all to this Heisenberg's talk show today. And Ms. Sarbani Chatterjee, who is a PhD candidate at IISER Mohali, is here to address you all. She will be exploring stuff, which she has bundled together in her presentation today. And our panelists will also be briefing you about what she is going to present. So without further ado, I think let's just begin. Yeah.
Okay, I'll share my presentation real quick.
By the way, Sarbani, I think we should, go to our panelists also because they have a brief information to give to our audience. So, if you may, please.
Yeah, sure. Yeah.
So, Heisenberg's The Physics Club of NIT-A, founded in 2021, is a bunch of curious minds trying to understand the intricacies of nature using mathematics and experimentation. We strive for making the best out of our club and its members by providing an open and welcoming environment to debate and discuss the ideas and innovations in the field of physics and allied fields. Amongst various in-club as well as open activities, we organize talks with science communicators by inviting professors, postdocs, PhD scholars, and competent students.
So after a brief about the club, we have then Asa coming in. So Asa, what do you?
Our speaker for today is Ms. Sarbani Chatterjee, who is majoring in physics from Indian Institute of Science Education and Research, Mohali. She will be sharing with us the science of everyday observation to the exciting domain of quantum physics and superconductors. She'll be now beginning her presentation. We'll surely have a great time here.
Yeah,
Yes.
Sarbani, you can go ahead. Yeah, we are all
Yeah.
ready.
We are all interested, excited.
So, can you all see my screen?
Yeah, we can.
Yeah. Yes. Is it?
About my field of research specifically, but to share with you some of the very interesting problems.
There's a glitch. Can
I
you
think,
fix this?
Sarbani, you can just, go to a better signal strength place and then we can begin because I think there is a small glitch. Okay.
Okay, I'll try that. I'm sorry for this.
Yeah, now the audio is fine. I think you can speak.
Okay, then maybe I'll keep. Hello?
Yeah.
Yeah, sure.
Yeah. You can go ahead now. Now it will be all right. You can start. Mm-hmm.
Uh, so, yeah, I don't know where I got cut off, but let me repeat myself.
Yeah, sure.
So, I am pursuing my PhD under Professor Arvind, and the main area of my research is quantum optics, and I shall not be speaking much on my research topic specifically. of the in the vast array. So I hope all these talk master your rest of it. This will be followed by a few examples from our everyday lives, from our surroundings, and those situations that we witness almost every day happening. Discuss a few interesting topics that are currently very popular in the field of research all over the world. And lastly, I shall explain the basics of my research field and discuss some results obtained in my work on quantum Stirling heat engine. This will not be an entirely technical talk involving understanding of equations and rigorous theories.
You are तेरा
So, mostly I shall include introduction to the many interesting physics problems that I have come up. Please feel free to listen. So, what exactly is physics? It includes space and time, and also the related entities of energy and force. Physics is one of the most fundamental scientific disciplines, and its main goal is to understand how the universe behaves. Now, what does physics mean to you? Would anyone like to share their thoughts on this?
Since no one is answering, so let me go ahead. So, basically, I think, in my
Anyone?
perspective, physics is about, a mathematical modeling, or
Sure,
maybe
go
a
ahead.
simulation, which can be extrapolated to experiments and then can be retraced back. And basically, then it covers all of science on a large scale, on a macro scale. But we also divide it into other branches. Maybe goes some part of that goes to biology and goes to ribosomes, those biomolecular machines. Those also have a lot of physical understanding from biophysics perspective. And then we see core physics in its rampant theory form when we go to relativity and all that. So yeah, that's from my side.
Yeah, very wonderfully answered. So, to most people who are not into physics, think of it as a subject which involves just dealing with a whole lot of difficult looking terms related to each other by a whole lot of scary looking equations. But in reality, those who love physics know that physics is is a lot more than just difficult looking equations and terms, as very nicely explained just a few seconds ago. Now, there are a few people that we cannot ignore. We have here Sir Isaac Newton, who is credited for formulating the laws of motion and universal gravitation. He is responsible for the classical theory of electromagnetic radiation. This was the first theory to describe different magnetism as different manifestations of the same phenomenon. Now, we all know this person here, Albert Einstein. He is best known for his developments in the theory of relativity. He has also made important contributions to the theory of quantum mechanics. Now, up next is Richard Field formulation of quantum mechanics, the theory of quantum electrodynamics, Another works in particle physics. Oh, well, we cannot forget Werner Heisenberg in today's talk, right?
No, no, never,
So,
never, never.
he
You
was one
cannot.
of the key pioneers of quantum mechanics. Yeah. So, he devised the matrix formulation of quantum mechanics, and he is also known for his contributions on hydrodynamics, atomic nucleus, ferromagnetism, and many, many more. Well, there were not a lot of women working in physics back then. We recall Marie Curie, who was the first woman to win a Nobel Prize. She is known for her pioneering research on radioactivity. The situation is slowly changing in the modern world, and now we witness an increasing number of women scientists working at par with their men counterparts, which is really great. Okay, so now we can integrate all of physics into one big picture. So on the x-axis here we have time. Time near the origin, which fractions of seconds or microseconds or even smaller. And the processes which occur over millions of years are placed to the far right, away from the origin. Now, on the y-axis, we have the size or the scale of the process. Near the origin, we keep subatomic processes, and huge celestial bodies are kept farther away. Uh, yeah, so we can essentially place depending upon its size and time. So quantum mechanics is placed here at the bottom near the origin, and astrophysics and cosmology is placed at the top right. Now, in between these two major fields of physics, we can find all other physics. A few such everyday life physics examples that elevate my interests in physics
देखो
and
ऑडियो
maybe
कट क्यों रहा
yours
है?
too.
तेरा भी ऑडियो, इनका वॉइस इतना कट क्यों रहा है? उनका हो रहा
Okay,
है।
so now here we are given with two eggs, and we are told that one of the eggs is raw, while the other one is boiled with both eggs shelled. Okay, so what we have to do is to
इसका क्या हो गया? फिर
anyone, any guesses?
Give it to the head so that he can implement
Oh,
that.
okay, okay. Possibly we can do that too. Okay, so let me tell you a scientific answer to this. So,
Yeah.
in order to decide, we will spin both eggs on a table or on the floor or anywhere. So, we will notice that one of them spins faster than the other. Now, if we try to stop the rotation by simply tapping both eggs very lightly, we shall see that one of them will stop rotating almost instantly, while the other will still continue to rotate. So now we can easily guess that the egg which rotates and stops easily is the one which is boiled, and the other which rotates slower and also does not stop instantly is the raw egg. So how did we conclude this? Well, this is nothing other than the concepts of inertia and angular momentum. So the boiled egg being solid throughout, it starts and stops rotating very easily. As for the raw egg, when it rotates, we are essentially only moving the shell. So the liquid inside, which was originally at rest, tries to maintain its state, and so it opposes the rotation that we had applied to the shell. So this is the reason for the slower rotation of the raw egg. And this same reason applies to when we try to stop the rotation as well. So we all enjoy swinging very high, right?
Yes.
So a swing is and we have all come across the formula for its time period. So we see that the time period of a pendulum is independent of the mass of the bob. So that means the time period of a swing does not depend upon the mass of the person swinging on it. It depends only on how high or how low the bob or the seat of the swing is from the point of suspension. So interesting, right?
Yes.
Yeah.
Yes.
So, next, let us discuss about the angle of repose.
यार ये भाई
We have all seen huge heaps of sand
ये
piles
हाइजेनबर्ग सर सबसे
near
बोरिंग टॉपिक
construction
है
sites,
अभी
or
तक आगे
even
देखते हैं
wheat and flour heaps when we try to make rotis or puris for an appetizing lunch or dinner. Maybe when we don't want to have our mess food. So now, the angle of repose of a granular material is the steepest angle of descent or dip related to the horizontal plane to which a material can be piled without slumping. So it is basically this angle here. So at this angle, the material on the slope face is on the verge of sliding off. So if you continue to pour more and more sand, the pile will continue to grow in size. That is, both its height and radius will increase. And so its shape will remain intact. Why? Because the angle of repose, the pile shape or the angle of repose will be different if we use a different granular material to make a heap. Okay, so let us now talk about a few very interesting theories and experiments that are being researched widely and are of interest to many researchers around the globe.
Yes.
Okay, so we have all heard about the Schrodinger's cat. It is basically a thought experiment that illustrates a paradox of quantum superposition. So this deals with a hypothetical cat which is trapped inside a box that may be considered simultaneously alive and dead as a result of its fate being linked to some random atomic processes or subatomic processes that may or may not occur. So, similar to the Schrodinger's cat, there are quantum particles that can exist in a superposition of states at the same time and collapse to one of the constituent single states upon interaction with other particles or even when they are viewed by an external observer. So, to make it simple, let us think of a system to be initially in some state A. Okay, and if we measure it, uh, we will get one particular result, let's say alpha. So again, consider a second system B, which gives a result beta when measured. Now, what do you think will happen if a system is in a superposition of these two states, A and B? So the simple answer is that the result will be sometimes alpha and sometimes beta. So which will be according to a probability law. Okay, depending upon the relative weights of A and B in the superposition process. Okay, so let's move on to a few more interesting topics. So, as the name suggests, a room temperature superconductor is a material that is capable of exhibiting superconductivity at room temperatures, that is above 0 degrees Celsius. Now, superconductivity is the ability of certain materials to conduct electric current with practically zero resistance. Now, only at temperatures below a certain threshold temperature or critical temperature, these materials will show superconductivity. Yeah, another interesting property of a superconductor is that it shows Meissner effect. That is, the magnetic field is expelled out of a superconducting material. Magnetic field lines have to pass from around the superconducting material and not from inside it. So this makes it possible for such materials to levitate. It would be amazing to read more about in free time or whenever. So another interesting ongoing research is on the fast radio bursts. So these are transient radio pulses of lengths ranging from a fraction of a millisecond to maybe a few milliseconds as well. So what are these basically? These are bright and unresolved occurrences that span over a large range of radio frequencies. So these bursts have enough strength to stand out from the noise source. Noise may be from the cosmic ray background or from any other phenomena that is happening around. Okay. So these bursts usually appear as a single spike of energy without any change in its strength over time. Because these occur as isolated phenomena, the nature of the source that produces them remain inconclusive. A magnetar, which is a type of a neutron star, has been identified as a possible source. Another possible explanation is a collision between very dense objects, like those of merging black holes or maybe neutron stars. Uh, some groups also believe that these signals might be artificial in origin, maybe from some extraterrestrial source. Another interesting research topic is entanglement and teleportation. So, quantum entanglement means that multiple particles are linked together in such a way that measurement of one particle's quantum state determines the possible quantum states of the other particle. So even if the entangled particles may be separated by thousands and thousands of kilometers, if we change one particle, we can induce a change in the other without even going near it or even touching it or even observing it. So Quantum entanglement has found several applications over the years, one of them being quantum cryptography, about which I shall come to later in my talk. So now, yeah, teleportation. So we all know what teleportation literally means, right? So many movies have used this as a form of superpower for their superheroes. But unlike in movies, each other, it is actually quantum information that can be transferred and not physical objects from a sender to a receiver several kilometers away. Okay, so now nonlinear dynamics is another very interesting branch of physics. It is actually an interdisciplinary branch, which also includes biology and sometimes maybe chemistry. So, yeah, that are governed by equations that are more complex than linear equations. So, let us talk about the logistic map. So, a logistic map is one that maps the population value at the next time step. Okay, so it is done in such a way that the population at time t plus 1 is equal to the constant of the growth rate. And this is multiplied with the population at time t and also 1 minus the population at time t. So this basically was a definition of the map that was used to plot this diagram. So this is the bifurcation diagram. This is called the bifurcation diagram, and it basically plots some of the growth rate. So if we now zoom into the growth rates between 2.9 and 4, so in this region here, we can see what is happening at a very fine scale. So it is possible to divide the population into two branches, that is 1 and 2 branches here. Just beyond the growth rate of 3.4, the diagram bifurcates again into four parts: 1, 2, 3, and 4. Now, if we move beyond the growth rate of 3.5, like somewhere here between 3.5 and 3.6, we can see that this bifurcates again into 8 parts: 1, 2 here, 3, 4, 5, 6, 7, and 8. So the system now oscillates over 8 population values. By the time we reach a growth rate of 3.99, that is to the rightmost end of this plot, it has bifurcated so many times that the system now jumps between all the population values. The system now has become aperiodic, but we should keep in mind that it is still deterministic. So we say that it has reached the state of chaos. Now, if uh, if we zoom in any of these two branches, say suppose the top branch, we see the same structure that we saw earlier at the macro level. So we see that if we consider only the upper branch, we see that one branch divides into two, which further divides into four, and then we slowly hit chaos, which was basically what we saw at the macro level from 2.4 to 4. So if we keep on zooming in infinitely, we will continue seeing the same structure and patterns at finer and finer scales forever. This will never stop. So this is a property that makes fractals so interesting. Okay, so now I shall tell you about my research area. I work on quantum key distribution. Basically, what the aim of quantum key distribution is to securely generate a secret key between two distant parties, say Alice and Bob. We also want the information to be safely transferred between them without any eavesdropper getting to know about it. Here we have named the eavesdropper as Eve. There are broadly three main steps involved in a quantum key distribution process. Uh, the first one is to prepare a state that is to be transferred from Alice to Bob. Next, the state is transferred through a quantum channel to Bob, and after receiving the state, Bob will then perform a measurement on the quantum state that he received. So this is followed by security encryption, which will essentially help Alice and Bob eliminate any differences in their respective keys. Now, I would just like to add one point here is that when
सेल्फी
the
ले
key is transferred from
एक
Alice
सेल्फी ले हम दोनों का वहीं से बैठ के
to
लेना
Bob,
मुझे
or then
अच्छा है
uses some sort of attenuation or defect into the key because of attenuation and all. So the classical post-processing steps essentially help us to eliminate those sort of differences that are caused because of that quantum
दिखा
channel.
कैसे
So yeah, these keys can
हिंदी
then be
अच्छा
used to encrypt information
रख से
that
बोल
Alice sends to Bob, and Bob can then decrypt the received data using
इनका
his
रिसर्च
generated
अच्छा
key.
है लेकिन करना कैसे
So
है
basically, what we did was transferred information
ये
securely
वाला
between any two
इम्पोर्टेंट है
parties
लाइक हर
without
रिसर्च इज क्वाइट
any third
इंटरेस्टिंग
party
ओके
getting to know about it.
बहुत ब्रेक हो रहा है कभी कभी समझ नहीं आता
हाँ
क्या हो रहा है
लेकिन इनका रिसर्च इंटरेस्टिंग
Okay, so another interesting topic on which I have worked on is the quantum Stirling heat engine. This schematic shows the PV diagram of a
कान में
degeneracy
टिन टिन लग रहा है
assisted quantum Stirling heat engine, where the harmonic oscillator has been used as a working medium. Uh, Analogous to a classical Stirling heat engine, a quantum Stirling heat engine is also a four-stroke regenerative heat engine. I shall come back to discussing this PV diagram later after a few basic concepts on heat engine in general. Okay, now heat engine is basically any system that converts thermal energy to mechanical energy. So generally, we illustrate a heat engine using the energy reservoir model. The engine is connected to two thermal reservoirs, one of which is kept at a very high temperature, say TH, and is a constant heat source for the engine. The other is kept at a very low temperature, say TC, and acts like a heat sink. So, the engine takes up energy from the source, uses part of it to do some useful work, and dumps the remaining energy to the sink. Thus, after completing one full thermodynamic cycle, we can write the work output of and the efficiency of a heat engine is defined as the ratio of the output to its input. That is work to the input heat. We should keep in mind that attaining 100% efficiency is not possible for a real engine. Okay, we now We all know the PV diagram or the pressure volume diagrams are primary visualization tools. If we plot a line that is perpendicular to the volume axis, it is called isocoric. In this case, we have dV equal to 0, that is volume equal to 0, and there is no work done in an isocoric process. And if we plot a line that is parallel to the volume axis, it is called isobaric, and dP is equal to 0 in this case. But here we have work done. Now, a process when there is no change in temperature of the working medium is called isothermal, and a process involving no heat transfer is called adiabatic. Both these processes, that is isothermal and adiabatic, have some work as output. So these are the basic four processes that are involved in any thermodynamic cycle. Okay, so yeah, the Stirling engine has a four-stage thermodynamic cycle associated with it. It has two isothermal stages and two isocoric stages. But as we just saw in the earlier slide, the isocoric stages do not have any the sum of the work done during the two isothermal processes only. That is during stages 1 to 2 and 3 to 4. Now, we know that the Carnot engine has the maximum possible efficiency and is an ideal theoretical heat engine. So, we might expect the efficiency of the Stirling engine to be much less than the Carnot engine. But ideally, this is not the case. Why? Because a Stirling engine has an inbuilt regenerator, which increases the overall efficiency of the engine so much so that it becomes very close to that of a Carnot engine. Now, a regenerator, as you all might know, is basically an internal heat exchanger or a temporary heat store placed between the hot and the cold reservoirs. So it simply retains some of the heat that would otherwise be dumped back into the cold reservoir as useless. So this extra heat then gets converted into some additional useful work, enabling the efficiency of a Stirling engine to approach the limiting Carnot efficiency. Okay, so before we move on, are there any questions or anything that you would like to say in between?
I think everyone would like to move on to that quantum one. Yeah, so that's it.
Okay. So then let's do that. Mm, Yeah. So till now we were talking about heat engines having gaseous or liquid working media, and now we want to bring in some quantumness into picture. So we can do this by considering an ensemble of harmonic oscillators as the working medium for our Stirling engine. So we all are well familiarized with a harmonic oscillator. It has equally spaced energy levels with a gap of h cross omega between any two consecutive levels. And the 0 point energy is at half h cross omega, and it corresponds to a quantum number n equal to 0. So now what happens when we try to insert an infinite delta function barrier at the center of a harmonic oscillator? So the potential of our new system will now have this extra added term. Here, P approaches infinity if we have an infinite potential barrier. So now comes the interesting part. When we insert an infinite delta function barrier, remember quasi-statically, at the center of the harmonic oscillator, it shall introduce a constraint on the probability amplitude of the wave function such that it goes to zero at the positions where the barrier is inserted. So the wave functions are modified so that they now have a node at the center. Okay, so now since the barrier is being inserted exactly at the center of the harmonic oscillator, in our case, it will only affect the wave functions with even quantum numbers. Why so? Because for even quantum numbers, we don't have nodes at the center. There are antinodes at the center for even quantum numbered energy levels. And those with odd quantum numbers will remain unaffected since they already have nodes at the center. So this causes the even numbered states to rise up to the next odd numbered energy state. So what this will do is basically give rise to a twofold degeneracy. So the new energy levels of the system then will be n plus half h cross omega, but with one difference, that is this energy will be only for odd energy levels. And we won't have any even energy levels this time because we will get converted or move up to the odd energy levels. I hope this part was clear for everyone.
Yes.
Okay. So now we shall move to the principal proposal of my paper that I had written with three other student authors, Chandan Kumar, Gurdeep Konar, and Sohini Chatterjee. So in this paper, we have studied a quantum Stirling heat engine with the harmonic oscillator, and we at stage 1 initially. Let us now insert an infinite delta function potential barrier at the center of the harmonic oscillator in a quasi-static manner. So we have just seen that this gives rise to degeneracy, and it is also shown here. So this basically is the meaning of degeneracy. So the even numbered and the odd numbered wave functions will overlap, and the insertion of an infinite barrier causes a node or creates a node at the center. Okay. So the classical analog of this step is the isothermal expansion, which is shown by this red arrow. Now, during this process, the harmonic oscillator is kept in contact with a heat reservoir so that it maintains a constant temperature throughout. So, we have now reached stage 2, and the harmonic oscillator is now connected to a cold bath, which reduces the system temperature. So, this is analogous to isochoric cooling for the classical engine. So, this brings us to stage 3. So, in this step, we remove the barrier quasi-statically, and the system is kept in constant contact with a cold bath. And finally, the system is detached from the cold bath and reconnected with the hot bath, which raises the system to its initial temperature. So the harmonic oscillator quantum heat engine has completed one full thermodynamic cycle. Okay, so let us now have a quick look at some important results that we had obtained in this study. So the first one is that work with KBTC since it makes it easier to work with dimensionless units. The second plot is for efficiency against TH by TC. Both these plots also include the effect of frequency of the harmonic oscillator, that is omega naught. Now, the extracted work is seen to increase from 0 and then they become asymptotic in the high dH by dC limit. But the efficiency, on the other hand, level off asymptotically to 0. So, this behavior of efficiency is in contrast to that of a classical heat engine. So, this basically is shown only by a quantum heat engine or a quantum Stirling heat engine and with a harmonic oscillator as a working medium. Uh, yeah, so what happens in a classical heat engine is that the efficiency starts rising from 1 and it it starts rising from 0 and it asymptotes to 1 for high TH by TC values. So the efficiency for a quantum heat engine is seen to approach the Carnot limit only for small values of Th by Tc, and the deviation becomes large for larger Th by Tc values. So this result can be seen more explicitly in in this plot on the right, where the efficiency has been normalized with the Carnot efficiency. So for small Th by Tc values, we can see that it is close to 1. So that means the quantum and the classical cycles have almost uh, uh, similar efficiency, similar nature. But as we move to higher Th by Tc values, we can see increase when frequency of the harmonic oscillator increases. So that when the frequency of the harmonic oscillator tends to 0, we shall approach the classical limit. So it becomes similar to a free particle in this limit, and so the work needed to insert or remove the barrier becomes 0, as is also evident here. So as we decrease the fields, and when it is almost 0, the work done also will be 0. Okay, so now I shall conclude this talk by stating this famous quote. Uh, Physics is the science of all the tremendously powerful invisibilities of magnetism, electricity, gravity, light, sound, cosmic rays. Physics is the science of the mysteries of the universe. How could anyone think it is dull? So I hope you enjoyed the talk and feel free to share what interests you in physics. Thank you.
Thanks a lot, Dee. So the first question that I would like to ask you, since you have come to an engineering institute, is that what's the application of the quantum Stirling heat engine? Like, how are we going to exactly model it in a real life and then, at least get some experimental data out of
Oh,
it?
Yes.
yeah. So, like I'll go to the slide here. This one. Okay, so a quantum Stirling heat engine, I mean, we use it every day, even in industries and all. So basically, if we use a classical Stirling heat engine, that too without a regenerator, we get a very low efficiency. Now the regenerator adds on to a better efficiency. But if we move on to quantum Stirling heat engine, what happens is that we are using various different working media. Like here we have used a harmonic oscillator. So
Okay.
as for your question, uh, uh, what am I going to say?
Yeah, like how
Yeah,
will
how
we?
do we implement?
Yeah, right.
Yeah. So basically, like this one was a theoretical model. Why? Because we inserted an infinite potential barrier. But if we try to implement it practically, we will not be able to achieve this. We will have some limit to the potential barrier that we insert. Okay. So now insertion of a potential barrier leads to degeneracy, like we saw in this slide. And this degeneracy mimics a classical Stirling heat engine. So
Right.
we can equivalently use a quantum heat engine to do the same work.
Hmm.
Okay, so here we have exploited the fact that we get degeneracy. But if we instead of harmonic oscillator we use something else, some other quantum system maybe. So there in that case, you may not see degeneracy. You may see some other phenomenon arising. So all these phenomenon will be in some way similar to or will mimic whatever the classical Stirling heat engine has to offer.
Right. So the next question is this: that since it is all about quantum, and there is a misconception, or not even a misconception, like about quantum mechanics, that it works on the scale of small. So, what is this like? The quantum heat engine, will it only be effective only when if implemented in some nano devices or things, or like can we make a car engine out of it if we try to mimic it, even if theoretically possible?
Okay. So if you want to try to implement it like uh, in for bigger objects like a car engine, so it will have somewhat different effects. Now, why? Because when we move on into the classical region, like bigger objects, we see that
Like,
and,
question,
and,
please.
and and if you want to compare it with the harmonic oscillator, we can see
Question,
that
please.
the frequency of a harmonic oscillator, when it becomes close to zero, we will go to the classical regime,
रोना आ गया.
right? So
अच्छा कौन
from
आया था?
this plot here, we can see that if we have a harmonic
कौन वाला?
oscillator with a frequency close to zero,
छला
we
नहीं
will
आया.
have no
Why?
work done. So if we try to implement a quantum harmonic oscillator quantum Stirling heat engine to a classical regime, it will not give us a great result.
Hmm.
So it's better, or
Right. Yeah, definitely, I get you. I think we might have some other questions from the audience. So, members from the audience, if you have any questions,
yeah,
you
sure.
can directly ask our panel. I mean, our guest for today, and I think she will be glad to answer that.
Yeah, sure, of course.
Okay, I think maybe people might not have questions in this. So maybe we'll wrap up this academic section. But I would like to ask some general questions, like a lot of a great
Okay,
number of physics students are sorry, engineering students are interested in physics. But given the statistics and data and employment situation in our country, a lot of students are not taking up physics at the undergraduate level or so. But since you said
okay,
about, say, the non-linear dynamics and all those, so those are very overlapped region with engineering and other sciences as well. So how would you like? What would you suggest to someone who is studying engineering and wants to do some physics internship and stuff like that? What are your advices for those people?
okay. I will put it in one simple line: follow your heart.
Yeah, I
So
think
you
that's a
you should
very
do whatever
powerful
you
line
do.
to speak.
Yeah. So even if you are enrolled in an engineering course and you want to pursue physics, or even the opposite, so either ways, it should not limit uh, your thinking or your interests, right? So you should keep on following and pursuing whatever you love to do.